All right, so today our lesson is not about paint format. Thank you. All right, so let's try it again. All right, so our lesson today is continuing on lesson 12, what happens when gases are cooled and heated. Today you're going to be watching our video lesson, and then you have a smaller homework assignment to do. I'm sorry, it was bigger yesterday. We're all still learning how to work this. And you'll have the reading 12.1 to do today, and there's a couple of questions. Not a big deal. Okay, so first thing we're going to do is look at the agenda for today. It is March 24th. And the first thing you're going to do is your bell work, which you probably already did. Then we'll have our video lesson that we're doing right now. And then your final thing to do today is reading 12.1 on Google Classroom. Don't do it on IQWST. Okay, I'm checking Google Classroom. So what I did was I put the reading in as a background, like we did on our interactive notebook slides. And so you can write directly in there. So make sure you do it there. So our objective by the end of this lesson, you'll be able to explain the relationship between temperature and volumes of gas. And you're going to explain that relationship in a familiar phenomenon. Okay, so reminders, make sure you turn in your assignments to be turned in for attendance. If there's a problem, let me know. I've already talked to a few people. We're still working out some bugs, so things are going to be a little bit more flexible for the first little bit. Okay, so let's go into our next slide. So warm-up questions. How does cooling and heating affect the speed of molecules? So stop and think about that. Okay, how does cooling and heating affect the number of collisions of the molecules? And how does the temperature affect how hard the molecules hit the surface of a container like a balloon? Okay, so number one, warm-up question. How does cooling and heating affect the speed of molecules? The more thermal energy that we apply to molecules, the more movement they have. Okay, so if I apply thermal energy to a water molecule, it's going to speed up. It doesn't get bigger, it doesn't get smaller. It goes faster and farther apart from each other. Okay, if I cool it down, if I take some of that energy away, like if I put it in a cold place or I put it in the fridge, or like we did with our balloon yesterday, we put it in the cooler. That definitely affected the speed of those molecules. That's why our balloon shrunk, okay? The molecules inside the balloon didn't change. They didn't change in number. There is the same amount of molecules inside the balloon from when I first put it into the cooler from when I took it out of the cooler. The difference was the cooling effect, okay? When we took the thermal energy away from the molecules, they slowed down and they weren't moving as fast. And our temperature went down. Okay, next, how does cooling and heating affect the number of collisions of the molecules? Okay, so let's stop and think about this. If I have a whole bunch, let's pretend we're in, our whole class is on the bumper car ride. You guys have played bumper cars before, right? Okay, I'll see if I can find a video to stick in here with that. So if we're going super slow, are we going to crash into each other much? No, we're not, because there is not that many, that's not that much speed, so there's not as many collisions hitting each other because it's just not going as fast. Now let's put it on fast mode. Okay, we are going like crazy. We're bouncing all over, and because there's so much more movement, we're going to be hitting each other more. Okay. How does the temperature affect how hard the molecules hit the surface of a container like a balloon? All right. Again, this goes right back to the other two. The temperature of the molecules gives it the speed. If it's warmer, it's going to have more speed. If it hits something with more speed, it's going to be harder. Just like if I was in a car. If I was in a car and I was going fast, when I hit something like a barrier or a wall or a bus, then that would definitely have a harder impact than if I was going really, really slow. Okay. All right. So let's look at our observations. This kind of ties back into yesterday. As the gas inside a balloon is heated, the speed of the particles of the gas increases. We observe this as an increase in the temperature of the gas. Okay, so thermal energy is not the exact same thing as heat. They go side by side. Okay, when you have one, you have the other. But they're not the same exact thing. When we have the balloon inside, when the gas is heated, the speed of the particles speeds up. So the molecules are going faster and they're hitting the sides faster. Okay. And this is going to make the volume of the container have to, if it can, let's try that again. When the molecules are hitting the side of a container like a balloon that can stretch, it's going to make it bigger. Okay. When it is cooled, the molecules aren't hitting the outside as far, and so it's just going to kind of collapse down inside of itself. It's kind of like, remember the parachutes that you guys used to play with in PE? That's really fun. So if I have everybody holding it up tall and having lots of motion, it's not going to fall down much, is it? But if I have everybody run inside and then it just kind of sinks down, okay, it's because it's taking up less volume. Hopefully that's not too confusing. All right, as the speed of the particles increases, it leads to stronger collisions between the gas particles and the balloon. Okay, this makes the balloon stretch and makes it larger. It also increases the volume of the balloon. Now, some of you are like, okay, what is this border? What's with the raft? And how does that? That's not a balloon. So, I haven't been able to tell you my stories for a while. So, this is a picture of a whitewater raft. Some of you have seen them, and some of you haven't. What some of you don't know about me is I used to work at a Boy Scout camp up in Idaho, and we used to take people on river rafting trips, just like this one, and they were a little bigger. Now, when we'd finish for the day, we would have to pull them up on the shore, and we would have to actually take out some of the air inside the boat, because it's a pump-up boat. We'd have to take out some of the air, because if we left it inflated all the way, when the sun hit on it at night, it would make the boat swell up and it could pop it. Okay, it actually happened that they had ruptured a couple of their boats, and so whenever they would pull up for the night, they would have to let about a fourth of the air out to keep it from expanding to the point where it would damage the boat. Okay, this happened because when the sunlight hit the sides of the boat and it heated up the air inside the boat, okay, it let the particles increase in speed, stronger collisions between the gas particles and the boat, and it would make it stretch. Okay, and when something stretched to the point where it can't stretch anymore, all righty. So now, as the gas in the balloon is cooled, the speed of the particles in the gas slow down. We see this as a decrease in temperature because we're taking away thermal energy, and so that makes the temperature go down. Remember, they go together. All right. So how can we apply this to things that we see? So I have my little popcorn. Really cute. Okay. Did you know that popcorn actually is a fantastic way to show this phenomena? It is, I promise. Okay, so let's see what is inside popcorn. This is a very basic diagram of popcorn. So on the outside, you have the shell. So the orangey part is the shell, and the inside has cornstarch and a little bit of protein and moisture and oil. Okay, that's where corn oil comes from and cornstarch comes from. And I added this little one, so we have some moisture inside the kernel. Now, the moisture normally is all the way through it, but this time I'm just putting it down here. So what happens is when I apply thermal energy to the popcorn, the water inside the popcorn kernel is going to turn into steam because the heat is making the water molecules move faster, and then it's going to change its form from a liquid to a gas. And what is it that we have a gas with water? Steam. So when the steam inside here, the pressure builds up and builds up and builds up, and then all of a sudden it can't take anymore. And just like our balloon, it pops. Okay, now I have a very, very serious video for you guys to watch about this. All right. The story of the cute little popcorn kernel. Here we have our cute little popcorn kernel. So cute. Inside the seed, there is a small amount of water molecules. Then our cute little popcorn kernel meets up with thermal energy. The thermal energy causes the water molecules to move faster until they turn. Sorry, technical difficulties. They turn to steam. Even though there are the same number of water molecules, they are spreading farther and farther apart. So it's not more molecules inside our little kernel. They're just spreading farther apart. This continues until the molecules move so fast and hit the outside of the kernel so much that it pops. So proud. That's my girls. Okay, so this is actually pretty cool. This is a slow motion real popcorn. Okay, and so let's watch what's happening. And if you look, you can actually see the steam releasing, okay, after it ruptures. Do you see the steam? Okay, that came from the water vapor inside the popcorn kernel. Wild. Okay, so I got this from YouTube. This is from a website called Warped Perception, and they do a lot of slow motion films that are kind of cool. All right, so these are our standards that we covered today, and I hope you guys have a great day. It was really cool getting to see you earlier today when I filmed this. I miss you guys a lot. Remember, you can all do hard things, and I have faith in you.